And welcome, everybody. I'm glad we have a crowd, and it's my great pleasure to introduce Antoniette Grima. Antoniette got a bachelor's degree at the University of Malta, and then obtained a master's degree at University College London, and subsequently worked on her PhD with Carolina Lithgow-Bertoloni, who at the time moved to UCLA. Antoniette joined us a while ago, but thanks to the pandemic, most of that was virtual, and so she worked out of the London office for a while. And I'm glad that worked out in the end, but she managed to move here last fall, and it's great to have her around. Antoniette is a solid earth dynamicist with broad interests in the connections between the deep mantle and the surface. In particular, she's an expert on subduction dynamics, which she's going to talk to us about today, but she also has interests in the tectonics of Europa, and it's great to see a bunch of you guys signed up to chat with her, and hopefully this can be a start of sustained collaborations with folks here at UTIG. But her talk today is on subduction dynamics, and I'll hand it over to Antoniette. So thanks for joining us, Antoniette, and welcome.
So thank you so much for that lovely introduction, Thorsten, and thank you for inviting me to give this talk. Can you see my screen?
Yes.
Okay, perfect, thank you. Right, so today I will be talking to you about subduction, and this is a process that is uniquely distinctive for the Earth. And it is one way through which the surface is transported into the mantle and can interact with the interior of our planet. And now, saying that sentence, I've just made subduction sound extremely simple and straightforward. But as we all know, this is actually not the case. And subduction can be very complicated and very variable. And we can see some of this variability in this figure from Hayes and co-authors from 2018, which shows the present-day active subduction zones and the geometry of the slabs at their trenches. And we can see that, for instance, some subduction zones, like the one here in Mexico, has very shallow slab dip angles, shown here in these yellow and orange contours. Whereas other subduction zones, such as the Tonga, for instance, have very steep slabs, shown here in these purple and dark blue colors. And based on this wide Banai of zone geometry, we can broadly group subduction zones into two main end members. So subduction zones with a flat or shallow style of subduction, and subduction zones with steeply dipping slabs. And then connecting these two end members, we have these intermediary slabs. Now, not only can we notice that we have distinctly different subduction zones, such as the Marianas, for instance, and Alaska, but this variability can also occur within the same trench if we keep an eye out for the different subduction zone names I'm showing you here on this plot. And a great example of that is South America, where we have examples of both flat slab segments here and here, and steeper dipping slabs along the same margin here, here, and here. Now, this is important and has a first order influence on the topography of the overriding plate, which I'm showing you here for South America. And we can notice that the topographic signal, or the deformation, for those flat slab segments is distinctly different from those where we have a steeper subducting slab. We can also notice that there is a difference in the band, or the width, of this deformation on the overriding plate close to the trench. Now, this variability is something that doesn't only occur across different subduction zones. It's not only a spatial thing, but can also occur back in time. And this is beautifully illustrated by the northwestern margin of the United States, where in the past, in this region, we've had a flat slab episode. So essentially, the subducting slab switched its dip angle from something like this to a morphology that looked more similar to this cartoon here shown in slide B. And essentially what happened here is that as the slab angle decreased, we've had significant deformation and uplift of the overriding plate, and that resulted in the Rocky Mountains and the Colorado Plateau. And eventually, as the flat slab episode became extinct, we've had this increase of the slab dip angle again. However, the overriding plate deformation remains and still remains to this day. So this implies that we really need to understand the dynamics, the initiation, and the causes of flat slab dynamics. And this is actually a project that Thorsten and I and Claudia are also involved in, looking at flat slab evolution in South America, under Colombia specifically. This also then begs the question, what controls this subduction style? Why is it so variable? Why do we have these different slab dip angles? And is there any one controlling factor? Well, that's a bit tricky, but we do know that most of these shallow dipping subduction zones have really high trench retreat, and this is quite common to these shallow dip angles. We also know from previous work that the thickness of the overriding plate is important, as one would expect from a plastically deforming slab. So this then implies that the type or the nature of the overriding plate is important. And indeed, previous work has found that previous work has found that the presence of a continental lithosphere can reduce the mobility of the surface plates. And this encourages the presence of single-sided subduction, which is what we see on Earth. Continents are also important, as we've just discussed, because they encourage a steeper subduction angle. And this is very, very important to get the slab to penetrate into the lower mantle. However, continents are also extremely complex. And we know this from seismology, geochemistry, and rock physics. And we can see some of this heterogeneity, which is represented in variations in viscosity and strength and chemistry in this S-wave velocity map from Pearson and co-authors from 2021. And if we had to look at the North American continent, for instance, we can see that there is this sharp gradient in S-wave velocities as we move inwards towards the colder, older continental crater. Okay, so subduction zones are complicated. But then how do we get to study them? Where are the hints? What do we do so that we can understand them better? And one tool that we have at our disposition is the surface geology. And this gives us information both about things that are happening now, but also about things that have happened in the past, as we've just seen for the North American continent, for example. And we can also combine this with seismic tomography. Seismic tomography models give us a present-day state of both the slab and the mantle. However, we're missing a link between the two. How do we go from here to here? And the connection is numerical, and the connection lies in these high-resolution numerical models. And this is what I use in my work. I use 2D numerical models of subduction and using the code aspect, to which we solve for the conservation of mass, momentum, and energy. And our models have a composite power law rheology. We also include plastic yielding. And we also include in our models an adaptive mesh refinement. And what this is an ability that allows us to really zoom in and focus on those zones in our model that we are interested in. So we have very high resolution in the at the surface of our model, within our continent, and around the slab. And in these regions, we can easily go down to resolutions of 1 kilometer. And our models also have implemented a free surface. So what this means is that the very top of our model can deform and deflect and change as the slab subducts and the dynamics of our models evolve. And so combining this free surface with this adaptive mesh refinement, we are then able to resolve the very high resolution, even the small scale fluctuations at the top of our model. And these models are run on Frontera, which is next door to UTIG, which is the fastest and largest supercomputer in the world. Okay, so what do these fancy models look like? Our models at the top are free, are not attached to the side, so both the subducting plate and the overriding plate are free to move, and we have a viscosity jump at 660 kilometers depth. And at the beginning, we have fast slab sinking in the upper mantle, followed by anchoring, and then slab sinking in the lower mantle and slab rollback and trench retreat at the surface. But what is interesting is something that's happening here on the overriding plate. So let's zoom in a little bit and focus on that. And this area in our model is the equivalent of a back arc region on Earth. And back arc regions are, again, very diverse, as we can see by this map from Hurrett and Lallement from 2005, which shows the different back arc regions for different subduction zones. And regions where we have extension are shown in blue, whereas back arc regions dominated by compression are shown in red. And Hurrett and Lallement found that there is a relationship between these two styles of back arc deformation based on the overriding plate motion and the direction of that motion. They also note that this behavior is also dependent on the slab behavior at the trench. And once again, we go back to the style of subduction, and we find that slabs which are flat or close to the surface are linked with extension, whereas steeper slabs are linked with a compressive back arc region. But we've also just discussed that the continents are very heterogeneous and that the properties of the continents can make a difference both in terms of the evolution of the slab and perhaps might even influence the topography. So then how does this play, what role does this play then in the evolution of the back arc region? So to answer that question, I am going to start off by showing you a very boring heterogeneous continental overriding plate. And what you can see here is the topography, the viscosity, and the strain rate. And now on the right, I'm going to show you the exact same model, but this time around, we've implemented some heterogeneity in there in the form of this high viscosity or stronger continental keel. And just by boiling these two figures, we can immediately see that the slab morphology looks very similar, right? However, the viscosity and the strain rate do not. And this is reflected in the surface topography. Okay, but this is just one time spot of within our model. How does the topography evolve through time? And this is what I'm showing you over here for our homogeneous continent. And this is our topography. On the y-axis, we have time, and on the x, we have distance. And anything that is blue or white represents topography below 0 kilometers. Anything that is brown or green represents topography above 0 kilometers. And if we look at the model evolution at this stage, we have the slab in the upper mantle, and we note that there is a drastic increase in the trench retreat rate. As the model evolves, the slab anchors into the lower mantle. We have a slight decrease in the rate of trench retreat, but this remains continuous throughout, even as the slab sinks into the lower mantle. If we look at the topography of the overriding plate, we can note that there is a general shallowing of the overriding plate, and there is a general trend of tilting of the continent towards the trench. And this is particularly evident towards the end of the model. Okay, so then what if we had to introduce some heterogeneity? What would the topography look like? And this is the answer. So in this case, we have, again, heterogeneity in the form of a higher viscosity continental keel, and we can see immediately that the topography looks very different. In this case, we have the formation of a well-defined foreland basin. And if we compare, again, the model evolution in the upper mantle, we can see that we have a similar slab morphology, and similarly, we also have this sharp increase in the trench retreat rate. But if we look at the topography on the continental overriding plate, we notice that this time around we have much higher topography, and we also have the incipient formation of a foreland basin. Moving on, again during the anchoring phase, we see a slight decrease in the trench retreat rate, but we still have this consistent fast trench rollback. And if we look on the overriding plate, we see now that our basin has grown both wider and deeper. And this trend continues even in the later stages of our model when the slab is in the lower mantle. We have the same trend for the trench retreat, and the overriding plate shows this deeper and more extended foreland basin. Okay, so then what would happen if we had to increase the extent of this heterogeneity by making the continental keel even longer or bigger? And we can see that when we do that, the region that now is occupied by our foreland region is even bigger. We can also notice that the trench retreat is considerably larger, and as is the rate of the trench retreat as well. And if we look at the slab evolution in the mantle, we notice that this time around, instead of the usual anchoring, we have slab flattening at 660 kilometers depth, which is then followed by slab avalanching into the lower mantle. Next thing that we try is we test changing the properties of the continental keel, the properties of this heterogeneity, by changing its density. So we went back to a smaller continental keel, but this time around it's more dense. And we can note that we still have this very well-defined region. However, the foreland basin is narrower and less deep compared to the two previous cases. If we look at the trench retreat for this case and compare it with the homogeneous case, we notice that the homogeneous case has the least amount of trench retreat compared to this case and compared to the two previous other cases with heterogeneity. And we can immediately notice that the model with the largest extent of heterogeneous continent also has the biggest amount of trench retreat. Okay, so let's look at these models together. And what I'm showing you here is the topography and the slab morphology for our homogeneous case at the top left, and the cases with heterogeneity on the right and at the bottom. And the first obvious conclusion, just by quickly eyeballing this figure, is that the slab morphologies look eerily similar, but the topography does not. And the second conclusion is, just by looking at this figure, is that we need heterogeneity to be able to form this foreland region. Continents which are homogeneous do not have a well-defined foreland region. Okay, so now let's focus on the two most interesting models, and let's start with the higher density heterogeneity. And in this case, when we have a higher density continental keel, we notice that apart from the formation of this foreland basin, we also have two bands of topographic highs, before and after the basin. And then all of this is followed by a flattening or a lowland formation. And this is comparable to the topographic signal that we can see in Peru, for example, and in Colombia, where we have these topographic highs, or this deformation front with intramontane basins between them, and then followed by this lowland region. The second thing I wanted to point out was the case with the highest amount of heterogeneity. And what we can see is that the bigger the amount of heterogeneity that we have on our continent, or the bigger the extent of this heterogeneity, the bigger the foreland region, and the higher the amount of deformation and extension. Now, this points to a very subtle point, and it implies that heterogeneity allows for the partitioning of the plate velocities across the subduction zone. And when we have heterogeneity, more of this partitioning is occurring within the foreland region, hence the extension, hence the deformation. And the more deformation, the more extension that we have in this foreland region, the higher is the amount of trench retreat. Okay, so far we've been looking at the very surface, at the very top of our model. But what's happening within the continent at this foreland region? And what I'm showing you here, is a map of is a plot of the horizontal shear stress. So anything that is in red represents compression, whereas anything that is black or gray represents extension. And we can see that throughout the model evolution, our foreland region is constantly in extension. And if we compare the thickness of this foreland region, so from the top to the bottom of the continent, and we compare it across the 4 different cases, we can see that the model with the most homogeneous continental overriding plate has almost no variability in thickness. Important to note, which is not plotted here, all of the models start off at 150 kilometers depth. Oops, sorry. All models start off at 150 kilometers depth. What we can note is that for our models with heterogeneity implemented in them, all of these foreland regions become thinner and thinner over time, which implies that this entire zone is being deformed and is undergoing extension, not just at the surface. Okay, so then what happens if we had to increase the deformation in this foreland region and increase the plate partitionings within this part of the overriding plate? What would the topography look like? And this is what this model is showing you over here. So the first thing that we can observe is that we have extreme rates of trench retreat. We still have the formation of a foreland region and a foreland basin, and this is considerably extended, particularly towards the end of the model. But we can also see that this fast trench rollback is allowing for the spontaneous development of a flat slab, which in turn affects the continental overriding plate and increases the deformation that we record both in the foreland region, but also further inland, where we see the secondary subsidence on top of the continent. Okay, so this implies that the type of overriding plate and the interactions of the overriding plate with the subducting slab can have an influence on how the slab develops and on the dynamics of the slab within the mantle. And we know from recent advances or so in the last couple of decades or so in seismic tomography that the mantle is full of slabs of different types and sizes and found at different depths. And we can see some of this complexity in this cross-section of a P-wave model by Foucault and Wouters from 2009, which shows slab material all the way from all the way at the surface at the trench down to the continental boundary. And sometimes slabs sink into the lower mantle directly without too much deflection. At other times, they flatten at 660 kilometers depth, similar to what we can see here for the Japan slab. So then this begs the question, what controls the slab morphology and why are slabs so different at different subduction zones? Well, the first agent that determines the slab behavior is the slab buoyancy and the slab strength, right? But as we've also seen, the overriding plate type is also a major influence. And similarly, we also need to keep in mind the effects of the phase transitions as we go from the upper mantle to the lower mantle. And we also need to keep in mind that variations in mantle viscosity can also interact with the slab and affect its evolution in the mantle. And this work is not something new. It has been looked at in the past, and actually seminal work has been done by Christensen in 1996, which shows that the evolution of the slab in the mantle can be determined by the amount of trench retreat at the surface, as we can see for slabs with a fixed subducting plate and slabs where the subducting plate is allowed to roll back and retreat. Christensen also showed that slab morphology can be affected by the nature of the phase change at 660 kilometers depth. And we can see that different trench retreats and different properties or densities and collateral slopes of the phase transition from ringwoodite to bridgemanite can change the dynamics and the shape of the slab at the top of the lower mantle. So we wanted to take this a step further, and we now include a continental overriding. Sorry, we now include an overriding plate, which was missing in the previous cases. And we wanted to explore this interplay between the buoyancy and the strength of the slab with the viscosity structure. And we start off by looking at the slab dynamics with a mantle where we have the phase change from ringwoodite to bridgemanite and ferroporite clays occurring at 660 kilometers depth, concurrent with a viscosity jump. And we see that in these cases, the slab flattens at 660 kilometers depth. Now, keeping the same model setup, but replacing the overriding plate type with a continent, we can see that in this case, the slab tip manages to penetrate into the lower mantle. So this confirms what we've been talking about at the beginning of the talk, right? Then we also wanted to compare how a different viscosity structure might influence the slab evolution. And what we do here is we implement a viscosity structure based on the latest gravity inversions from Rudolph and co-authors from 2015, where we have a phase change at 660 kilometers as required by the numerical physics, but the viscosity jump occurs at 1,000 kilometers depth. And once again, we notice that we have this slab flattening and deflection at 660 kilometers depth. Next, we keep everything the same, so the same viscosity structure, the same slab, the same initial conditions, but we change the overriding plate type. And we notice that this time around, the slabs looks rather different. And instead of the flattening that we saw before, we see this slab tip penetrate into the lower mantle. Okay, so why? What's happening? What's the difference between these two models? And what I'm showing you here at the top is the induced viscous flow for a slab with an oceanic overriding plate. And we can see that the flow has a horizontal component already before the slab sinks into the lower mantle. So the slab has reached 660 kilometers depth, and we see that the induced viscous flow already wants to deflect it. And this is even more pronounced as more and more slab material sinks through the upper mantle. Eventually, this forces the slab to deform and bend and deflect on top of the 660. However, However, when we have a continental overriding plate, we can see that the induced viscous flow in this case has a much stronger vertical component. And this drags the slab below the phase change into the lower mantle. We can also notice that at this stage, the trenchward motion of the continent induces a shearing of the upper mantle towards the slab. And this drag and shearing towards the slab forces the slab in the upper mantle to deform and deflect at 660 kilometers depth. So we end up with a slab that's simultaneously deflected at 660, but with this anchoring into the lower mantle that's slowly dragging the slab body into the lower mantle below 660 kilometers depth. Right, so as we can see, simply changing the overriding plate type changes the induced viscous flow, the dynamics, and we end up with a very different slab morphology at the end. Okay, so to better understand how the slab morphology is changing through time and how the dynamics are evolving, we now consider measuring the ratio of the deep slab angle, so at the tip of the slab, and the shallow slab dip angle close to the trench. And we call this ratio SB. And we find that when SB is bigger than 1, the slab is in its juvenile stage. And this is a stage that is characterized by a very steep slab, a lot of penetration through the mantle, and a lot of slab rollback as well. As the slab matures, we notice that SB gets closer to 1. And we also note that the slab morphology changes from this curved type to a more straight morphology. So the slab in this stage has undergone bending and straightening out. And this means that the slab has undergone a lot of deformation. This stage is also characterized by decreased penetration to the mantle. Eventually, the slab reaches an old age where SB is actually smaller than 1, and this stage is characterized by very little to almost no slab penetration. Instead, we see that there is a lot of slab flattening, and now the slab travels laterally on top of the 660 instead of vertically downwards into the mantle. However, when we have a continental overriding plate, instead of going through this old age, we go to a rejuvenation stage. And in this case, we see that SB has increased again to bigger than 1. We have a slab tip, and this slab tip is pulling the rest of the slab above it slowly below 660 kilometers depth. But this has to, and renews the penetration to the lower mantle. But this has to compete with the flattening and retreating of the slab that's also occurring above 660 kilometers depth. Okay, so we have looked at how slabs can be both flat at 660 kilometers depth and how perhaps they can also sink into the lower mantle. But seismic tomography also indicates these strange anomalous features which are found at the top of the lower mantle, and they don't seem to have a very obvious direct connection with the surface. So what are these fragmented slabs and how did they get there in the first place? And the current interpretation is that each individual slablet represents a subduction regime that is now extinct. So if we had to take, for instance, this red slab over here, the tip of the slab represents the initiation of that subduction regime, whereas the top of the slab records the age of the cessation of that subduction regime. And the length of the slab can therefore give us an idea of how long that subduction regime was active for. With the cessation of this subduction regime, we must have had some overhaul of the overall tectonic regime at the surface and the reorganization of the plates so that we could have a new subduction regime start and therefore have this subduction of additional material above our fragmented slab. So based on this interpretation, then we can get an idea of how things looked like in the past, right? So if we were to take the slab fragment, for instance, we can easily reconstruct it to the mantle by simply dragging it upwards until at some point it impinges the surface. And then we can assume that at that point, that is the location of the paleo trench of that subduction regime that now is extinct. And this is a very interesting idea. However, this is an interesting idea that has been used to reconstruct the locations of these paleo trenches, the location of the paleo continents, but also to map out the paleo plate motions. And this is an interesting idea that's also very useful for us to understand how things have changed in the past on the Earth's surface. But it comes with a number of caveats. The first thing that we need to keep in mind is that this assumes that trenches are stationary. And we know from geology, from analog and also numerical models that trenches are not stationary. They tend to retreat or advance, but it's very rare to find a trench that hasn't moved throughout Earth history. The second assumption is that all of these slab fragments must come from a break-off in the slab that occurred close to the surface, either due to necking or stretching or through the decapitation of the slab by a continental keel, for example. And then obviously, once we have this shallow break-off, then subduction must terminate, must stop, because we have removed this negative buoyancy that's dragging the slab downwards and driving subduction. And the last assumption is that subduction is vertical. So this means that we assume that the slabs fall directly and linearly under the trench. And therefore, we can easily reconstruct this vertically upwards. However, we know from, again, our numerical experiments and our analog experiments, but also if we had to look at seismic tomography, we know that this is not the case. And a lot of the times, the tip of the slab is found several hundreds of kilometers away from the expression of the trench at the surface. So then this begs the question, is there any other way? Is there any other interpretation? And we, again, go back to our trusty numerical models. And this time around, we again look at subduction in a 2D numerical model, but we implement a low viscosity layer between 660 and 1,000 kilometers depth. And this is, again, motivated by the geo-8 inversions and by recent mineral physics studies that indicate that there should be a superplastic layer below the phase transition. So then what does the slab do in this case? And we can see that we have subduction, the slab sinks below 660 kilometers depth, and then it breaks directly at the top of the lower mantle. So this is very interesting, but what is really going on? So let's zoom in and have a look. So we can see that prior to orphaning, as the slab sinks into the lower mantle, the slab is one coherent hole, shown here in orange. During the orphaning stage, the slab has sunk below 660 kilometers depth, so it has undergone the phase change and is found at the top of the lower mantle. And we can see that something very interesting is going on within the slab at this point. Here, the slab hasn't yet split, it hasn't yet separated, so it's just being a little bit strange. And then eventually it splits into a separate flattened parent and an abandoned orphan below it. Okay, so clearly this is the interesting stage that we want to look at. So let's zoom in a little bit and let's look at the density. And what I'm showing you here is a plot of the density of our model actually. And you can see that within the cold slab core, we have a lens of buoyant material. And this buoyant material is the result of the temperature dependence of the Clapeyron slope. So what this means is that the cold interior of the slab hasn't yet transformed into the high density bitumenite and ferropericlase. And since it is more buoyant than the surrounding material which has transformed, it is therefore resisting subduction and therefore causing the slab up tip of the 660 to undergo compression. However, we need to keep in mind that the slab tip, which has already sunk into the low viscosity layer, has transformed, so it's denser, but it is also sinking at a higher velocity because there is less resistance to its sinking speed. And this therefore means that the slab tip is under tension. So this is then causing the slab to stretch and deform, right? So for instance, if I had if you could see my arm and I was pulling my palm downwards, but someone else was pulling up from my wrists upwards and my arm could deform plastically, I would end up separating my hand away from the rest of my arm. And this is what's happening to orphaning. However, there's also another step, and that is the induced viscous flow. So when the slab first sinks into the lower mantle, the induced viscous flow has a very strong vertical component that's helping to drag the slab into this low viscosity layer below 660 kilometers depth. However, once the slab tip is below 660 kilometers depth, we can notice that the induced flow in the upper mantle goes in the opposite sense as that induced in the lower mantle. So this deformed and stretched slab is essentially being sheared by this opposite sense of the flow in the upper mantle going against that in the low viscosity layer. And eventually this stretching and shearing of the slab leads to the formation of a parent slab that has abandoned its orphan below 660 kilometers depth. Okay, so what I'm showing you here is a regime diagram. It's actually a plot with the slab yield stress on the y-axis, and you can think of this in terms of the slab strength. And on the x-axis, I'm showing you the Clapeyron slope. So the Clapeyron slope essentially determines how much material can sink below 660 kilometers, because it determines how much material can transform at this depth. So think about it maybe perhaps as a force that is resisting subduction. And what you can see plotted in these red diamonds are slabs that flatten above 660 kilometers depth. And in magenta, you can see slabs that have penetrated below 660 kilometers depth. And these are all slabs that are subducting in the same viscosity profile. So we always have a low viscosity layer between 660 and 1000 kilometers depth. And right in the middle between these two different slab morphologies, we can now plot orphaning. So orphaning fills this intermediary space in our subduction regime diagram and connects these two end members that we see in seismic tomography. And orphaning does not occur only for one type of slab. We can see that strong slabs can orphan, as can weak slabs, and also these intermediary slabs. And what is interesting is that orphaning can link these two morphologies. So this is one of the biggest questions in geodynamics. Are these penetrative and flattened morphologies related? And if so, what is the link between them? And actually, a slab that is orphaned is one that starts off its life as a penetrative morphology. It undergoes orphaning and then ends up as a flattened slab. So this is one way through which slabs can mode switch to adjust to changes in the relationship between the slab strength and the strength of the mantle. Okay, now this is not just an exploration of the parameter space. We think that subduction, that orphaning actually occurs at subduction zones on Earth. And an example of this would be, for example, the Japan slab and the Tonga, where we can see this deflected, flattened slab, parent slab, overlying the abandoned orphan below it. And this is important because at the end of the day, the mantle and the slabs within it are a record or a history of plate tectonics at the surface. And this is clearly affected, as we've seen, by geodynamics at different depths. And this is a very useful tool, especially when we're trying to understand how plate tectonics changed in the past. But if we keep in mind the current interpretation that all of these slab fragments must be linked to subduction cessation, this leaves us with an interpretation of plate tectonics that's constantly stopping and starting. So the slab breaks, subduction stops, and then a new overhaul of the surface regime has to happen before subduction has to start again. Whereas orphaning provides us with an alternative interpretation that perhaps subduction doesn't need to stop and start so often, and instead these slab fragments are the result of orphaning at depth from the same parent slab. And this obviously then has implications for our understanding of the timing of island arc accretions and these shifts and changes in surface tectonic regimes. Also, as we have seen throughout the presentation, the overriding plate clearly plays a major role in both the deformation at the surface and in the evolution of the slab morphology at depth. And it's these continental properties, such as the thickness and the heterogeneity of the overriding plate, that are extremely important, and we need to really understand them, because these will determine how mobile or how stiff the overriding plate is, with implications for the subduction style, but also this has implications on the survival of the craton and on then the influence this has on the evolution of mountains and formations of basins, such as the ones we see in Colombia, for example. And all of this would not be possible, this understanding would not be possible without these high resolution free surface models, which allow us to link the interior of the planet with the exterior of the planet and understand how these two work together to form landscapes at subduction zones. And with that, I conclude and say thank you for your attention.
Thanks a lot, Antoniette, for a great presentation. I guess we can all do our virtual clappy hands here, and obviously exciting stuff. We have time for questions. If you want to raise a hand, I'll try to monitor this here. Okay, all right, cool. Let's start with Duncan, please.
Hi, yeah, that was a really fascinating talk. For the first part you're talking about, how sensitive are the processes to erosion and sedimentary processes redistributing mass?
I'm sorry, I think you must have cut out for me. I only...
The question was, how sensitive are surface processes such as sedimentation, redistribution of mass to affect topography, from what I understood?
Right. So we do not currently implement erosion or the deposition of material in our models yet. So I cannot answer that question. And it is something that would be interesting to implement and to look and see how this in turn affects both the uplift, but also perhaps even the deposition of sediments at the trench, and seeing that variability in thickness and in viscosity, but that's not implemented in our models just yet.
Thanks.
David?
Yeah, thank you for that talk. There was a lot to think about there. And the one thing that I was really thinking about is how effectively your model showed how heterogeneity in the continental crust affected the results. But yet you didn't put in any of the known heterogeneity that we see in oceanic crust. So in your subducting slab, you have these huge swaths of slab that have what appear to be constant properties. And if you took what we know from ophiolites and from modern seafloor studies and you put in variability in strength or variability in temperature and composition, what might that do to your model results? Because we know something about those things. Yeah.
Right, so that's a very interesting point actually, and you're right. Our slab has a constant age, and it's relatively bold, and it's very homogeneous. But yeah, that would be an interesting point to include and to model. We have only added heterogeneity in the overriding plate because so far every subduction model, numerical model, always includes a very homogeneous overriding plate, and we wanted to see if adding heterogeneity makes any difference to the topography, which we see it does. But it would be interesting to combine heterogeneity for the subducting plate as well and see what difference this makes to the overriding plate topography, for sure.
Thank you.
And I mean, I guess sort of the difference is a little bit in terms of the age, right? Because the oceanic lithosphere is going to be, for the most part, determined by its age, and it's fully recycled every 100 million years or so. But then, of course, the crust, the oceanic crust, might be variable, particularly in terms of the sediment coverage, for example. So you would change the interface properties probably more.
Yeah.
But like the deep oceanic plate, it seems sort of hard to think of relevant heterogeneity besides the age variations, right? If you're subducting a ridge or something like that.
Yeah, or more maybe like an oceanic plateau, for instance, or something like that. And we actually do change the interface properties. So this is, let me go back. So this is what, oh, can you still see my screen?
Yeah, but it's still the, yeah. So it's the thank you slide.
So I'm trying, no, sorry, my monitor is playing up and I'm getting like a black screen every time, which is not great. So if we go to this slide, for instance, this is what we are varying over here. So we have varied the strength of the crust, of the crusty layer, and we see that when we do that, this allows for these higher trench retreats at the surface and the spontaneous development of this flat slab, right, with consequences for the overriding plate topography. So we do still see this basin, but then we see this secondary sort of deflection of the continent behind the foreland region. But we haven't changed the properties of the subducting slab.
Brian, please.
Yeah, I enjoyed the talk, and I really appreciate the starting points where you showed the modern flat slab subduction in South America and perhaps the most famous example from North America. I was struck in that part of the talk where you were discussing extension, that somehow these models were actually predicting in the foreland some type of extension, because that would be at odds with what we see for the flat slab regions in South America today, and then what we can infer from the geologic record for for the laramide system in North America for the 80 to 40 million years ago in the geologic record?
I think I'm sorry, I think my
So
connection is a bit unstable.
No, the question is, where does the extension come into play in your modeling?
Right, so the extension comes in, so if we look at this, in this case down here, like where we can see the slab evolution, it comes in from these fast slab sinking speeds at the beginning, which, so the continent is coupled with the retreating slab, and as the slab retreats, there's this stretching, there's this extension in the overriding plate. That does not mean to say that the continent has entirely thinned out and we now have, the formation of new oceanic lithosphere in there. It's just that the continent is becoming thinner. So if I go back to this slide, you can see that when we introduce heterogeneity, we have this thinning, this extension here in the foreland region. That's where the extension is coming from. And that is what's causing this essentially flexure behavior in the topography.
Yeah, Brian's point was mainly that this is not what we see geologically. And I wonder, when you go back to your other slide, where you have the flat slab, where you just showed the movie. Yeah, so I wonder if you go to a later stage, like sort of now, in this part, right, where the slab is sort of squished underneath the continent, like the proper continent, do you have like secondary phases of compression or something like that at these later stages? Like if you were to look at the deformation state above the dark blue thing, are there later stages of compression?
So that would be somewhere here. And there is compression, right? Because like the topography is increasing. So there is this dip, and then we can see that like inland of that dip, the topography is increasing again. So there is compression over there. I don't have the horizontal stress plots for this one, but I would say yes, based on the topography.
So it all happens like away from that plot, and we have to wait a little bit to answer Brian. Yeah.
Well, I would just finish to say that it sets up some really interesting predictions that we can test in the geologic record. Thank you.
Thank you.
Yes, awesome. Afu, please.
Yes, thank you. So you talk about the deep subducting slabs and consider the clay-prone slopes over a range of parameters. So my question is, when you took that into account, are you thinking about like there are different types of materials there that would actually affect the clay-prone slope, or you're just kind of considering different uncertainties there?
So the clay-prone slopes that we test here in this figure, I'm assuming this is the figure you're talking about, right? So we go from the clay-prone slopes that is suggested by current literature, right? So some people have suggested that the clay-prone slope should be somewhere between 0.5 to -3, and that depends obviously on the properties of the multimineralic slab, but there is uncertainty in the integrated value of the clay-prone slope at 660 kilometers depth. So we have tested these different ranges of the clay-prone slope between what is currently in the literature. But it also accounts for slight variations in the composition of the slab as well. This is based on a slab that we would assume is entirely made up of olivine, right?
But you're using basically a single phase transition, right? Where you're trying to capture the actual complexity with one number.
Exactly. Yeah.
And so that single transition is from basically this would be for the Lumutite to Bridgman plus ferrocarricate.
Yes, yeah, that's correct.
we have a question from the chat that asks about what would the effects of decompression melting be the overriding plate, right? So you get extension, you might that might lead to decompression melting, and that might lead to weakening the overriding plate and perhaps some sort of feedback, right? So what would happen if you were to include magmatic processes? That's how I understand the question.
Well, I think the answer to that would be extension. So as we know,
like, would it be enough to lead to decompression melting, and would the decompression melting enhance the extension?
I would say yes, it would, because if I go back, so this is a bit laggy because my internet is a bit unstable, but if I go back to this, if I go back to this slide and we look at the extension, at the extensive regime, we can see like how much the overriding plate is thinning by the end of the model. I think that would be enough to actually break the overriding plate. And it has been suggested by some previous work, by some previous studies, that if you have melting underneath the continental plate, you might be able to break the continents into these like slivers, continental slivers. But that would be another interesting thing to add to our models and to implement and see what the effects are. It's a bit tricky to do it with the free surface, but it would be an interesting venue to explore for sure.
Cool, thanks. Ian, and perhaps, this is one of our last questions, so out of time.
Just an observation. Are you hearing me okay?
Yeah.
Yes.
I'm just looking at a east-west seismic tomography of the adjoint tomography through the Scotia Sea. And just something you might like to look at there, the history of subduction that's going on today at the South Sandwich Arc goes back to about 30 million years. And there was a major move in the position of the trench at about 12 million. You can see the present slab going down to 400 kilometers from underneath the present South Sandwich Arc. And then the ancestral South Sandwich Arc, which was active from 30 million years forward to 12, you can see it separated and sitting down at about 600 to 800 kilometers. So it seems to me, in your terminology, an orphan, which is happily sitting. It hasn't sunk, apparently. But maybe that's a matter of time. Would it be a matter of time that it take longer to sink than 30 million years?
So from our models, we find that orphaning it depends. So the orphaning time depends also on the type of overriding plate. So when you have an ocean-ocean subduction, orphaning can occur within like 5 million years or so. But when you have a continental overriding plate, the orphaning stage is longer, and it can take round about from anywhere from 10 to 15 million years, 50 million years or so. But again, we haven't really tried different configurations of the overriding plate, so that could also affect the orphaning time.
Yeah. No, thank you.
Well, a stepchild kind of situation, not true orphan.
I'll send you, this is unpublished, so I'll send you the cross section. You can.
Yes, please. That would be very interesting. Thank you
That'd be
so
great,
much.
Ian.
All right. Thank you.
All right, folks. Obviously, Antoniette is around in Austin. Thankfully, there's a bunch of fun meetings hopefully this afternoon, but I'm sure she's happy to chat with you some other time as well. And so let's thank Antoniette again for a great presentation. And
thank you very much.
a great seminar. And thanks everyone for partaking in the good discussions. And,
thank you so much.
have a good weekend.
You too. Bye-bye.